In this video, we're going to talk about what the a value does when we look at it in a quadratic equation. So for the first thing you might notice is that here we've got a whole bunch of different quadratic graphs or quadratic equations, parabolas, whatever you want to call it, going through the same intercepts. And so the first thing that we know that we've identified with an a value is that if a is positive, if A is positive, then it's going to open up. So the graph will open up. So in this case, both the green in this case, sorry, the green here and the red here are both have a positive A. And we know if A is negative, then it's going to open down. So in this case, we see that the purple and the orange open down. But that's just part of the story for A because we can clearly see if all of these things go through the same intercepts, it's not just a matter of plus or minus because we would have the same x-intercepts and just a positive or a negative, then we would have just two options. We would have a negative and a positive. But here we've got two different positives and two different negatives. So there's something more to it than just being positive or negative. And what it is that we could actually have an infinite number of parabolas that go through these two intercepts or any two intercepts. The difference is the a value. The a value is what's going to lock it in, as I like to say, or what makes it the purple parabola, the orange, the green, or the red. So the specific a values will make this happen. So for example, maybe this is one of the parabolas that goes through here. Maybe this is 0.2 and this is 0.5 like we have right here. So when we look at this, the a value will say, okay, so we want the parabola that's going through 2, 5, that's also going to go through this point right here. And no other graph will go through this point. Only this one graph will go through this 0.04 or through this vertex. So so what we're going to do is we're going to determine how do we actually find that a value. Now, before we had noticed that when we had a factored form, and we say a, and sometimes we do x minus m and x minus n, we saw that these values were always opposite of these values right here. So if I'm talking about the m, typically I can take these intercepts and I can drop them in here, and I know that the values are going to be opposite of what's up here. And we learned why that was the case when we did the null factor law. So in this case, I see that I've got a positive 2 and a positive 5. That's what it says right here. So I'm going to make my m be positive 2. So I got y equals a x. Sorry, I need to make it minus 2 and x minus 5 because these values here are going to be opposite than what's shown right here. But now again, I could have an infinite number of parabolas that go through here. So how do I find out what this a value is? All I have to do is take another point that's not one of these 2 points and drop it in for my x and my y, and I solve for a. We know through all of the stuff that we've done with linear equations and all the algebra we've worked on, if you've got 3 unknowns, you're never going to be able to solve any equation as long as you've got more than one unknown. But since we can drop in 0.04, our y-intercept, in for our x and our y, 0 for our x, 4 for our y, then we can solve for a. We'll have that piece left. And then at that point, we know, okay, now we've got the equation for this blue parabola right here. So let's do that. Let's drop in 0.04. So what that's going to look like is, let's see, 4 is our y value. So 4 equals a times x we said was 0. Let's keep it the same color here. 0 minus 2 and 0 minus 5. All right, so 4 equals a times 0 minus 2 is minus 2. 0 minus 5 is minus 5. So 4 equals a times negative, oh no, not negative, positive 10. 2 times 2 or negative 2 times negative 5 is positive 10. Now I want to get a by itself, so I'm going to divide both sides by 10. And a, when I simplify it, is equal to 2/5. It's 4/10 here, 4/10, but know that we can divide both of those things by 2, so we end up with 2/5. So the equation for this graph right here is y equals 2/5. Notice it's positive because this is opening up. 2/5 times x minus 2, x minus 5. Oh, let me let's move this over here a little bit. X minus 5. So if I pick any x value along here, I'm going to find the corresponding y value. So it even looks like, hey, this looks like I might be able to find this. Let's see if this is 2 and that's 5. Let's see if we can find this axis of symmetry. Let's see if we can find this vertex real fast. So if we have 2 and 5, we can find the axis of symmetry. The axis of symmetry is going to be x equals 2 plus 5 divided by 2, which is 7 divided by 2, which is 3.5. So 3.5, yes, look at that. That's going to be our axis of symmetry. That's a very crooked axis of symmetry. That's going to be our axis of symmetry right here. There we go. So if I pick the x value for our axis of symmetry and I put it into my x values here, I will find the corresponding y value, which is our vertex. Remember, we know that our vertex is always made up of the axis of symmetry for our x and then whatever the y value is when we drop that back in here. So let's see if we can do this one real fast. I don't know if we're going to be able to. It might be kind of a tricky calculation, but let's see. So we're going to have y equals 2/5 times 3.5 minus 2 times 3.5 minus 5. And again, those 3.5s, these two values here, these are our axis of symmetry. So let's get those so we've got them color-coded. There we go. So those are our axis of symmetry. So now we just do our computations. Let's see, 2/5 times 3.5 minus 2. 3.5 minus 2 is going to be a positive 1.5. And then 3.5 minus 5 is going to be a negative 1.5. Negative 1.5. All right, so I'm going to need some help here. So let's bring over our handy calculator. See if I can move it over here. There. Oh. Geez, there we go. Okay. So, so we want to do 2/5. So let's do 2/5. What is that number? There we go. Alpha, this. 2/5 times 1.5 times negative 1.5. And we're going to get negative 0.9. So that means, what that means is we have our y value equals negative 0.9. And if we look right here, let's look at this a little bit closer. Look right there. That's just under or just above negative 1. So that makes sense. So our vertex is going to be our axis of symmetry, 3.5, and our y value that corresponds with that, negative 0.9. So what we can find is with our a value, not only does it lock in which quadratic we're using, but it also helps us find the other pieces. Once we have that a value, we can find any of the other pieces. Now, one other thing I want to say about the a value real fast, and that is we write our factored form like this. And then we write our standard form. Our standard form sometimes looks like this. Y equals ax squared plus bx plus c. Notice that this, of course, this is different from up here. But notice here our x's all represent dropping in an x into this whole thing. Our y's represent the outcome of the same y, so those two things are the same. But the b and the c are different than the m and the n because they're not going to be the same values. But if you look real closely, and I'm sure you don't even have to look that close, the a value is exactly the same in both of these. So that means that if you know the a value in your standard or in your factored form, you know the same a value is going to be in your standard form. So these two things are the same. They're not the slope, so don't get confused with that. But what they do is they lock in to a specific quadratic graph or quadratic equation.